So this is minus 1 parity of Ku, parity of Ku plus 1. And then I add the bracket. And the tensor, of course, of the tensor. So the definition says that I have a tensor with this disordered adjacent pair. I substitute the switch, the pair switch in that position, and then I sum the bracket. This in case 1. In case 2, I do something very... So it is defined by recursion again. So every time I have L, so two possibilities. Either happens this or this. So this I set it equal to, in this case I assume I'm in case 2, which means that both these are odd. Okay. So this is the definition. So I have 2 questions for them, not to the people that know. The first question is, why does this L solves the problem? Second question, if it solves the problem, what do we have to do? It's finished. So why does it solve the problem, this L? It obviously solves the problem. Why? It's linear, want to define linear match doing this thing. Because I want to ask the question because there are so many formulas on the board that one may get dazzled and not recognize the obvious thing and the non-obvious one. So why does this L proves it? Oh, si sono addormentati. They fell asleep when I said the case 1, they were just already asleep. Why? Ogni tanto ti sveglio. È una domanda facile, eh? Sì. Perché? What do we have to prove? We have to prove that the ideal intersect the standard, the order monomials is only 0. What did we have here? What does this L do? No, sono proprio addormentati. There are obvious things and non-obvious. We must concentrate on the non-obvious. This is obvious, so let's get rid of the obvious. Ma cosa fa su T0 e cosa fa su I questa L? On D0, what does it do? Is the identity on D0. What does it do on I? Cosa fa su I? Fa 0. E allora obviously they must be disjoint because I cannot have an application that is the identity and 0 simultaneously. Right? No. Okay, so we know that L has no problem at all. If we can define it, we're fine. But we have defined it, so the proof ends here, right? Because we have defined it. Why the proof doesn't end here? Why here is only the start of the second part?
L could be defined if those were the bases.
No.
We have to check this way.
Ma sei con la seconda fila, non dai retta.
Che io mi considero così ignorante.
What is the problem with this L? Unfortunately, Martha could not help because it was inside the identity. No, I have the same. Non mi fanno star zitta mai. First of all, Lorenzo claim is wrong because he did the same psychological error as Fabrizio, thinking you are already in UG. You are not in UG, you are in DG. So by no means T is a basis. You have to define for all possible, right? So you cannot say, it's, oh, I define it only there. No, I have to define for everything. Now, what is the problem? Correctly, Marta said, we have to prove it is well defined. What is the problem? Because one can say, no, it is well defined. I mean, I define for disordered, it's fine. The problem is that I'm making a very precise choice. I'm choosing one possible disordered pair, and nothing guarantees me that if I don't choose a different one, I get a different definition. It is the trick. So we will see this is not the case. So we have to prove this is the and if you look at the diamond lemma, the content of the diamond lemma is exactly this one. Diamond lemma is more general. It is worried about what is called the resolutions of ambiguities, exactly this problem. Saying if I order in one way or another way, do I get the same result? This is the key to the proof of Poincaré. The rest is only talking. Because yes, I forgot the number because I'm like this with permutation, reorder here, reorder there, but this is only things that sitting down one could do. This is the idea. This is the idea in the proof, this reordering instance. Now, I didn't do the calculation because I said I got bored, I have to do it now. First of all, we have to agree, convince ourselves that if we choose disjoint pairs, meaning that the pairs have no elements in common, and we reorder this and then that and vice versa, it will not affect this formula. You see what I mean? So, I want to make an observation, I don't want to make the calculation of this, because it's... so the observation is this: if I'm having a situation where T is... so I have two pairs, one here and one here, that are separated. For me, it is clear, but I urge you, if it's not clear for you, to make the calculation that if you first apply L and switch this, and then you reapply L and switch this, you will find the same as switching first. You see the point? Because they are disjoint, so they will not be affected by which one you do first. And if you see this, right? So this gives no problem. Or, okay, so that doesn't matter. So the only problem that we obtain is then when there is what the Diamond lemma calls an overlapping ambiguity. Yeah, no, so stay.
If I have a tensor and I apply L with respect to the first pair, I get something.
Mm-hmm.
If I apply L...
No, then apply also...
I say that if I apply L twice, this is well defined.
Yes.
L is not
No. It's no. I want to... The problem is this. Here, defining L in this way, I'm making a choice. I'm saying, let's find one that is not, one pair. Okay? and we switch and we define L like this, then this L is inductive, is one less of B, and so we have it already defined. This is the definition recursive, okay? Unfortunately, this definition depends on the fact that I pick the first to start, whatever, right? This is the problem. What if I choose a different one? Okay. Did I obtain the same? So I'm claiming that if I have two, I mean, if I have one only, okay, goodbye. I have only one choice and it's simple. But if I have two that are disordered, I apply L and switch this, obtain something. Then I apply L again and switch this. Then what I obtain is the same as doing the switch, okay? Because L is defined in terms of L. That is the annoying thing, right? That is a key point in this. So we are left to the case that we have only case to worry. I like only because it's not only, it's a lot. Is that you have x, k, u. So we have some, say, okay. So we have a tensor where we have a disorder pair here and disorder pair here. So we have to reorder this pair. So we have that Ku is greater than Ku plus 1, is greater Ku plus 2, and of course we have to separate in two possible cases, right? The case where you have no repeated, right? Because the problem that we did, case 1 and case 2. This is the case, this can be even and odd, but we can also have the case where Ku is equal to Ku plus 1, right? So, and also this is the same. Okay, so we have to consider, so we have to worry about this case. So what one has to do is very patience. The whole time is very rule. So what one has to do is to be patient and try to do this. So let's give a name to this, say called X, Y, and Z. At this point we need. And then we try to work it out using this definition. So the proof is very long, but maybe I'll start and then I explain what is that you have to do. So you have to reorder this, so making a choice that you first reorder these two, and then, so what do you need to find? You need to get Z, this is what you need to find at the end, right? And you start by reordering these two, and you obtain some expression, and then you start reordering these two, and you obtain another expression. Are these expressions equal? The problem is that they will be equal, but only with an application of the Jacobi identity, okay? So, between the brackets. Now one may wonder, are we using the ideal? No, we're not using the ideal, we're using the Jacobi that is identical 0, it's different. But at least I want to give a start to this. So, can we ask, no, we cannot assume we can forget about the sign, because the sign is important. So, and then we do L. So this is the first, let's call it A. So this will obtain the first expression for this. Now we do the other one. So, and then there is the bracket. Okay. So now, so we obtain this. We need to switch. See, this is ordered, so we have no choice in this expression. We need to reorder this. So it is very stressful. No,
can I make a comment now?
No,
it's not true that you don't have a choice here, because you may decide to exchange Z with something else, with what is after.
No, okay, yes, but I'm saying I'm considering this overlapping ambiguity.
Yes, but then at the end, you have to justify that you can reduce to this.
No, the problem is that you have two ways to go from XYZ to
the
ZYX.
But you, in the definition, you are not, you don't have to go necessarily from ZYX to XYZ directly. You can do other steps in the middle. The only thing that you want is that at the end all the variables must be ordered. So what I was saying is that you are using the fact that two reduced expressions in a symmetry group are linked by movements of this type, either a commutation among two disjoint letters or braid moves of this type.
No, I understand
This is not
what
either.
you're
This
saying.
is a big theorem.
No, I understand what you're saying. You're saying that, if I understand correctly,
Yes.
that in some sense we're using a representation of Sn, using its presentation as braid.
Exactly.
I'm not sure I agree with this.
But why do you have to exchange X and Z now?
No, because as
Because in
Franco
the
is saying,
definition of L,
Franco
you
is
can
on
do
my
other
side
things.
this time, so let's take advantage of this rare instance. No, it's because what I want to prove is the resolution of ambiguity. I have two things at this to start with. No.
But then you have to explain me why, if I do another exchange here, I have the same definition.
No, but no, I disagree, because here I'm saying at this point, defining L, I can switch these two, or I can switch these two. And what I'm saying is like I get the same result. I'm not sure I buy this objection about the. Is a way how do I start this the resolution of this expression. Then yes, there might be garbage, rubbish here. I don't care the rubbish. I reordered this. I have a choice and I show the choice doesn't make a difference. I don't think braid comes. I don't know. No, honest, I don't think it is.
You only need to show that there's no ambiguity for those very specific rules.
Right.
That's the point. You don't need to worry about in the middle if something more complicated happens, only this elementary.
This is siamo già contro uno, però I agree.
Okay, no.
No, I agree mathematics is not democratic. You may be right and wrong. No, I will think, but I don't see how this is a problem. The fact that you need to take the fact that it is true for the good permutation you need to worry about 3 only. This is the argument. But here I don't think you need to know this fact about permutations. Why should you know?
You may decide to use another to solve
yes, but
another.
this is a different
version.
problem because we're trying to solve the resolution of that type of thing. What is here, I mean, we don't worry what is it.
So you have to be sure that you have either this or the other.
What do you mean either this or the other?
Either a braid move or a commutation move. This is your starting point.
No, my starting point is like This case we don't worry about, and we excluded and left it as exercise because it's very simple.
Yes.
When the two are disjoint. If they're not disjoint, you're gonna fall into this. What else? There's no else.
Yes. Ok, go in the bush.
No, me la scassi, ma...
No.
Okay, so let us make this little calculation. So you need to switch this one. So parity of x, parity of z, and so y, z, x. And then I need to add the bracket. So it is y, x, z. And I don't forget this other bracket that is still here, sitting here. Okay. And then I do the last one. I need to switch these two in order to find the whole thing right. So it is parity of y, parity of z, and then there is this L of finally z, y, x, and then I have the bracket plus and then what is left. Then the other that we have to compare. So we start not from x, y, but we start from y. And then did I put everything correctly? Okay, speriamo. This is L of x times zy. I forget the sign. The bracket. Okay. Then I have to switch these two. I forgot the signs there. I forgot the sign. I realize now. So here I forgot the signs because so this one has no sign, but this one has a sign, right? Thank you. Because I realized it seemed to me there were no signs enough. So here, see, I forgot the signs because when I switched, there was this -1 multiplying all of this, right? I forgot sign. And also here, right?
No.
Wait.
The basic one was
One moment.
sign.
Yes, no sign, no sign.
Sign.
Then this, and then there is this as 2 sign, -1, I forgot. Because otherwise it won't come right. And here I need -1, parity of x, parity of y. I forgot the signs here and there. I explained here what happened also there, I forgot. So, see, here, because I'm working this expression, right? And this expression is multiplied by the sign z and y, right? So here I have zy and I have to add the switch sign. Here, but here multiplies the sign, so I just forgot. So this is, I switch X, Z, I forgot. And then there is this one, plus I, last one. And then we switch these two, so we get -1 and we get it ordered finally. And then we need to add the bracket. Then to copy the rest. Okay, finally the comparison. Okay, let us compare and hopefully they will get. So we have to compare A is equal to B. This is the point, right? A must be equal to B. So let us see. We have the first one, yes. This is easy. This one is equal to this one. Goes away. Then what do we have left? So this is so this must we have to rewrite everything.
How can we use Kobe? We must place us in a position to use.
Yes, we have to. How do we use? Irritating. Unfortunately, I got my book instead of Varadarajan, which is very bad because it is certainly explained less clearly. In fact, it says it is obvious. No, it is something trivial that is explained to me because. Cosa? No, è che l'obiezione sua, dai, non vale niente, quella la eliminiamo dopo. No, it's no, it's the problem that we don't want to use I because I is there's something silly here that I'm missing because here the Jacobi will give it if we know. You see, I mean, this is the. Okay, what do we have? Is because it is L. Isn't that because this, right?
The proof of this?
Huh?
This one, no.
No, I know it very well. I just it's a very stupid thing. This.
I mean, you have to get somehow a triple bracket.
Yes.
No, it is clear that there is a bracket here because, but we need to use the idea. That is the problem. That I think this is what is puzzling me, and I think also Franco, because
A triple bracket.
no, it's okay.
Because
We have it. No, it is clear what we have because here you see if you compare this expression, let's call expression A minus expression B. If you do A minus expression B, what do we get? But have to go tragically. So it is. You see, you pair these things. So you pair this with this, right? And then you pair this one with this one, and then this remaining one with this one, right? No, this is a mistake, obviously. There is a zip here, but it doesn't work. So, this will give you the Jacobi identity, right? But what confuses me is that modulo the ideal. That is the problem.
You know, L is 0 on the idea.
But yeah, we're doing it by induction, so we know that. We have to know this phi. We have to use the phi that is well defined downstairs. See, this is the key. Otherwise, you can't do it. Yeah, we're using the phi that here we lower the degree, so L is 0 on the ideal. Otherwise, it's so here we find L of. So let me write maybe the first one as this. There is a sign which I ignore. There is a sign here, just to show that it works. No, it's right. It's lower the degree. That's why. So you have yz times x minus x times yz is linear. Don't forget it is linear. So this will give me y z x, right? Forgetting about the sign. I forget about the sign now because, and then I have the other two, which will be, what is it, the second one, y x z. No, right, because it's lower, so it is well defined. There is induction here. Minus. So this is, all of this is y, x, z. And then there is the last one. It is x, y, z. And this is x, y, z. So up to the sign that you can check because there is this minus 1 to the parity, this is the Jacobi and it is 0. This is, I forget, L is 0 on the ideal, we're doing it on another induction. That is the key. Then there is the other case that we didn't do, the case in which there is a repeated. And it's the same. Now, Fabrizio, I want to think over what you say, but I don't think there is a problem, but I will think.
So, this is my point of view of the problem. You define L by an algorithm.
Yes.
So, you choose what is called a descent. You start doing the receipt. And then you go on until you get to a word which is ordered. But you can do it maybe in another way.
Yes, that's
using
a
another order of these elements. You have to prove that these two elements give you the same
Yes,
result.
that's the key of the proof.
But this is not what you have proved, because these two expressions may be very different, apparently.
Which expressions?
The order in which you solve the inversions.
Yes. But at the end, the result, I mean, you will have to get to the standard monomial.
Yes. But then, how can you apply this argument to this general case? You have two algorithms.
No, I apply it because I say that...
which look different.
No, because I'm applying an induction on, I'm assuming that when I lower degree, I have it defined. And I show that when I lower it, I can lower it in two different ways.
No, this is not what you apply. So, I can give an example.
No, I understand perfectly what you're saying. I know you don't believe me, but I understand. But
in these two expressions, the first elements that you apply may be very different.
Of course.
So how can you compare them? How can you compare these two algorithms using this?
But I compare only the first step of it. If I prove the first step, I get the
because you
same.
have two different.
No,
things.
but no, because if I prove you that after I move the first time, I get the same expression, then that's it, right?
But you didn't prove this.
I sort of think I proved it.
No, because maybe you have an expression that starts with S2, S3, and the other which start with X5, X6, S6. So why are they the same?
But you are reasoning in terms of permutations. I don't think this is the right way, because you are just no, because you have to reason about the disordered pairs. And so you're like, either my disordered pair is disjoint and then it doesn't matter because I obtain the same,
no, because,
or it's not disjoint.
No. The algorithm L depends on the order in which you decided to solve this.
But
inversions.
we prove that it does not depend on that order. That's the key.
No, you didn't prove this.
Then it's a matter of what I claim and what I prove.
You say you have an example.
Yes, maybe I can give an example. If you maybe.
No, but I understand what you're saying. It does not apply here.
So, tell me why your argument.
Forse io ho spiegato male questo sicuramente, però non è che non puoi applicare.
Suppose if you have this x2, x4, x3, x1.
Vieni perché dobbiamo finire.
You want to order this.
Devo andare con un altro posto. E allora Fabrizio.
So you have these two ways.
No, devi venire perché sennò io non faccio, devo scappare.
This means you first exchange these two and then S3 you exchange this, no, S2 is this two, then S3 is X1 and S3. Or you can do it another way.
Ho capito benissimo cosa dici, ma non sono d'accordo.
S3. Okay. So if you use this expression, you start applying the receipt L with S2, and then with S3, then S2, and then S1.
No, I'm moving just one step. After one step, the proof is over.
No, but this is a way to compute L. This is another way to compute L.
Yes, but I proved that the first step decides it. That's the thing that
The first step of what? These are two expressions, which are different.
I'm aware. I'm saying that I prove to you that after I do one step.
But
Yes,
one step of what?
Rita is saying that first you apply S1 in order to compute it in the first way, and then you look at what happens if you apply S3 in order to work in the second way.
Yes.
You realize that
That is the same.
if the starting point is the same, it is the same, you get the same result.
Exactly.
And then-
Without worrying about the permutations.
You have proved that if at the starting point you have S3, S1, then you can exchange them and it is
No,
the
it's a
same.
different-
No, because we do one step we lower. No, guarda, sicura, funziona. No, vabbè, adesso ne parliamo. però.
There could be another way to define an L. I think what Fabrizio is getting at is there could be another way to define an L that accomplishes the same thing.
Yes.
And
He's
you have
saying?
I think that's
No.
what he's wanting.
No,
The definition of L.
no, absolutely. L is defined in one way only.
Well,
That's-
no. L depends on the choice of the inversion.
But it will give you the result.
Yes, but then you have to choose an order of the inversions, to solve the inversions. And then at the end, you want to have the same result.
Sì, sì, dai, cioè, possiamo dare.
Cioè,
No,
non
sì.
ha fatto essere uno.
No, no.
Poteva essere uno.
Non si può andare per copiare.
Non ha fatto.